Pluto made them come all around Pluto's circle. Cross is that of one more planet. Pluto, the disappointing little planet at the outer levels of our solar system. Through planetary rap, it is stirring up force in the domain of space science. Propelling reports show an expected involvement with Neptune, raising concerns among experts and space enthusiasts. Clear figures like Neil deGrasse Tyson and Michio Kaku have sounded alarms about the repercussions of this grand cosmic event. Yet how did Pluto end up in serious comparison with its neighboring planet? Additionally, how might this incredible encounter affect life on Earth? Join us as we unravel how something tremendous just collided with Neptune, and why experts have been left restless by this massive anomaly. Pluto, once hailed as an evident planet, underwent a change in its status, being renamed as a dwarf planet due to its unique orbit. Despite this demotion, Pluto continues to captivate and intrigue the global astronomical community. Recent theories from respected analysts like Neil deGrasse Tyson and Michio Kaku have raised concerns about Pluto's orbit potentially intersecting with Neptune, suggesting an imminent series of interactions between the two celestial bodies. This could have significant repercussions for Earth. Pluto's journey around the Sun stands out due to its exceptional characteristics within our solar system. Its orbit is unusually slow, spanning a vast distance. Since its discovery in 1930, Pluto has yet to complete a single orbit around the Sun, adding to its mystique. The particularly elongated shape of its orbit deviates from the more circular orbits followed by the major planets. Furthermore, Pluto's orbit tilts 17 degrees from the ecliptic plane, giving it a more dramatic inclination compared to other planets. This combination of Pluto's inclination and its elliptical orbit introduces layers of unpredictability to its orbital pattern. One extraordinary aspect is its periodic interaction with Neptune's orbit. For about 20 years during each cycle, Pluto ventures closer to the Sun than Neptune, defying expectations given their respective positions in the solar system. Diving deeper into Pluto's orbit, it is fascinating to note that it is not a perfect circle but rather an elongated path resembling an oval. This unique orbit causes significant variations in Pluto's distance from the Sun throughout its journey. At its closest approach, Pluto lies about 30 astronomical units (AU) from the Sun, while at its farthest, it reaches over 49 Australian dollars, twice Neptune's distance from the Sun. Additionally, Pluto's orbit is tilted at a critical angle compared to the orbits of the major planets. This inclination not only adds complexity to its path, but also plays a crucial role in its interactions with other celestial bodies, particularly Neptune. When Pluto encounters Neptune, their gravitational influences adjust their trajectories over time. The intricate dance between Pluto and Neptune underscores the interconnectedness of celestial bodies, each exerting gravitational forces that shape the orbits of others. In recent years, advancements in observational technology have allowed astronomers to track Pluto's movements with unprecedented accuracy. This has led to a deeper understanding of its orbit and its potential implications for the stability of the outer solar system. While the likelihood of a direct collision between Pluto and Neptune remains low, the possibility cannot be entirely dismissed, prompting continued observations and studies by the astronomical community. Despite its small size and distant location, Pluto continues to command attention and interest among researchers and enthusiasts alike. The question arises, why hasn't there been a collision between Pluto and Neptune? The answer lies in the gravitational forces exerted by other planets. Astronomers began studying Pluto's path shortly after its discovery, and its orbit puzzled them. Unlike most planets that stay close to the same plane as they orbit the Sun, the ecliptic plane, Pluto stands out with its steep tilt and elliptical orbit. The mystery deepened when they realized Pluto's orbit crosses Neptune's. Despite these complexities, Pluto's orbit remains stable, showcasing the intricate mechanics of space. Understanding how three celestial bodies, Pluto, Neptune, and the Sun, move and interact gravitationally is a significant challenge. It's akin to predicting where they'll go based on their starting points and how they pull on one another. For Pluto, this challenge reveals how its orbit, Neptune's orbit, and the Sun's position all work together like a complex system. Terms like precession, libration, and VSOP variations help scientists address this cosmic puzzle. Libration ensures that when Pluto approaches Neptune or other large planets, it remains well above their orbit, reducing the likelihood of a collision. VSOP variations, named after scientists who studied orbital mechanics, explain why Pluto's orbit appears erratic but remains predictable over time. Despite the chaos in space, certain patterns and rules keep things in order. These principles stabilize Pluto's orbit, preventing collisions with Neptune or drastic changes in its trajectory. The possibility of orbital instability demonstrates how a celestial body's orbit is highly sensitive to its initial conditions. Researchers use computational simulations to understand how Pluto moves in space. These simulations use complex mathematics to model how Pluto interacts with other celestial objects like Neptune. By adjusting these simulations slightly, astronomers can see how minor changes can alter Pluto's orbit. In the late 1900s, these simulations revealed something fascinating about Pluto's orbit. Despite factors that should make it unstable, Pluto's orbit can still be irregular. Even slight differences in Pluto's starting position or speed can cause significant changes over many years. However, even with this unpredictability, Pluto's orbit remains stable for billions of years. This suggests that, despite appearing chaotic, Pluto's journey around the Sun follows a sort of pattern. Predicting what will happen with planets like Pluto, which have eccentric orbits, is challenging. These systems are so complex that long-term outcomes are difficult to predict. Simulations help us explore potential outcomes but also remind us that we cannot foresee everything. Understanding Pluto's orbit is crucial, especially when considering whether it could collide with Neptune in the future. This knowledge provides insights into how our solar system functions. Pluto's orbit teaches us that even seemingly unstable orbits can stabilize due to gravity. Moreover, the dynamics of space continue to surprise us, and studying these phenomena is essential for expanding our understanding of the universe and our place within it. When we explore space, we find that things can be strange, and Pluto's orbit is a prime example of that oddity. Pluto's orbit is unlike those of other planets. It is more oval-shaped, which means it is not a perfect circle. Sometimes it even comes closer to the Sun than Neptune does. This creates fascinating dynamics because, while Neptune is also moving along its path, there is a slight chance that Pluto and Neptune could text truncated for readability, crash eventually. In spite of its uncommon orbit, Pluto figures out how to keep away from Neptune most of the time thanks to what many refer to as gravitational forces. Gravity resembles an invisible power that pulls things toward each other. So, even though Pluto and Neptune could seem to be on a collision course, their orbits are carefully organized, coordinated by the pull of gravity. Pluto's orbit teaches us that space is full of surprises. What seems chaotic at first can be a delicate balance of forces. By studying Pluto's orbit, scientists gain insights into the intricate mechanics of our solar system. This continuous observation and analysis are essential to expanding our knowledge of the universe and our place within it. Imagine if Pluto and Neptune collided. It would be a cosmic event, sending shockwaves through our understanding of the nearby planetary system. While we've made progress in understanding space, this scenario suggests that we still have a long way to go. Focusing on how giant planets affect Pluto's orbit gives us critical clues about how our entire solar system functions. It shows us that where each planet is and how it moves can influence the paths of other objects in space. Despite the complexities of space, the possibility that Pluto could one day slam into Neptune concerns astronomers. This raises the question of why such a collision could happen, even though it seems unlikely. Neil deGrasse Tyson, a prominent astrophysicist, has some interesting thoughts about Pluto. He believes that renaming Pluto as a dwarf planet, rather than a major planet like Earth, is a step forward. He feels that we are continuously learning new things about how objects move in space. Tyson sees Pluto's odd orbit as a sign that there's still much we don't understand. He believes that the mysteries of space are fascinating and that significant events like Pluto's renaming engage people in astronomy. Tyson wants to help people understand the cold and sometimes strange aspects of how space functions. He emphasizes that studying space mechanics can astonish us. Tyson collaborates with other experts to warn people about the potential dangers of Pluto's peculiar orbit. After focusing on Pluto extensively, the possibility that it could collide with Neptune one day concerns him. He suggests that such a collision could create enormous problems for our entire solar system. An impact between Pluto and Neptune would be a dramatic and serious event, releasing a massive amount of energy and possibly destroying Pluto, with fragments zipping around space and potentially hitting other planets and moons. Neptune could also feel the impact, altering its orbit. Renowned theoretical physicist Michio Kaku, known for his contributions to string theory and science communication, offers an intriguing perspective on space exploration. He firmly believes that understanding the future of space travel and the connection between celestial mechanics and theoretical physics can be advanced by studying objects like Pluto. Kaku views Pluto's orbit as a window into the future of space exploration. By understanding the complicated gravitational interactions and orbital dynamics of celestial bodies like Pluto, we can improve future space missions, ensure safer navigation through the solar system, predict potential threats, and plan missions to distant corners of our vast universe. Kaku emphasizes that lessons learned from Pluto's orbit can be applied to studying other celestial bodies, providing a roadmap for decoding distant worlds. He often highlights the profound connection between celestial mechanics and theoretical physics, noting that the movements and interactions of planets, such as the gravitational dance between Pluto and Neptune, are rooted in fundamental principles of physics. Kaku's work in theoretical physics, particularly string theory, aims to unravel these principles at their core. He proposes that focusing on the complexities of celestial mechanics, like Pluto's orbit, can yield insights into the fundamental laws of the universe. Like Tyson, Kaku has also considered the potential consequences of celestial bodies colliding, relating it to his theories about the universe. A collision between Pluto and Neptune, while rare in cosmology, might offer a remarkable observational opportunity, contributing to our understanding of string theory. String theory, which replaces point-like particles with one-dimensional strings, seeks to describe the fundamental forces and matter in the universe. Such a collision could create extreme conditions of energy and gravity, shedding light on the behavior of elementary particles and forces under such intense circumstances. Moreover, the gravitational waves produced by such an impact could provide valuable data for testing string theory's predictions about spacetime. While the immediate impact on Earth would be minimal due to our distance from the outer solar system, the scientific implications could be significant. Understanding events like this could deepen our interest in the fundamental nature of the universe, as described by string theory and other areas of theoretical physics. Pluto's orbit, influenced by the gravitational forces of neighboring planets, especially Neptune, highlights the complex and dynamic nature of space. However, the universe holds many mysteries, and the three-body problem is just one of them. Scientists anticipate other potential catastrophes, underscoring the ongoing quest for understanding and exploration in the vast universe. Though it is highly unlikely, there remains a slight chance of planets colliding in space. This can happen because planetary orbits are influenced by various factors, such as gravitational pulls from other planets, a phenomenon scientists refer to as the three-body problem. In systems like the TRAPPIST-1 system, where there are 7 Earth-sized planets, the gravitational forces create a kind of dance in how the planets move, leading to orbital resonances. Over time, these resonances can make a planet's orbit less stable and potentially result in collisions. Although systems like TRAPPIST-1 are stable for now, scientists monitor these systems to understand how planets affect each other's orbits, especially when they converge. This helps us learn about planetary evolution in space. Sometimes rogue planets fail to orbit a star and drift through space randomly. These planets used to be part of a star system but were ejected due to gravitational interactions or when another star passed by. These wandering planets can cross vast distances and may collide with other star systems. However, since space is mostly empty, the likelihood of them hitting another planet is extremely low. Rogue planets are fascinating compared to the number of stars and planets with stable orbits, making collisions even rarer. When galaxies collide, it can disrupt the orbits of the star systems within them. Although planets may not directly impact each other during these massive events, gravitational interactions can alter how stars and planets move. Occasionally, planets are flung out into space, becoming rogue worlds. Other times they might collide with each other or their host stars. These disruptions can create new celestial bodies or form new stars. The late heavy bombardment hypothesis suggests that around 4 billion years ago, there was a period of increased impacts involving comets and asteroids. This bombardment is believed to have occurred because outer planets like Jupiter and Saturn were moving around a lot, disrupting the orbits of many smaller objects in space. These smaller objects were then thrown onto unpredictable paths, many of which ended up in the inner part of our solar system. This led to a significant increase in impacts on planets like Earth. While these impacts did not involve planets colliding directly, they showed how gravity can make massive changes to how things move in space. This bombardment shaped the surfaces and histories of planets in our solar system and may have even brought water and organic material to Earth, contributing to the evolution of our planet.